This meeting is being recorded.
In section 2 from chapter 14, we're going to review the specific type of bond stretching and bending due to a response of infrared radiation being applied to a sample that we may see. We're actually going to focus specifically on the stretching frequencies, and those are the ones that you are asked to be familiar with for tests and quizzes. But we'll also reference some of this bending type of vibrations that we might also encounter, such as in-plane bending, which is commonly referred to as scissoring. So these atoms would be bending in this fashion within the same plane. And then these guys here, these will be bending in and out of a plane here. So this is called twisting, as opposed to this scissoring technique or the scissoring action that we might see here. So again, we apply some type of infrared radiation to a molecule, and the bonds, the covalent bonds, will either stretch or vibrate in other fashions. So these are some common uses of infrared spectroscopy that you might already be familiar with. Night vision goggles can produce these types of thermal images, and not as common. We might see a less invasive type of detection for breast cancer through thermal imaging. But the textbook elaborates on why or why not this may be a useful technique due to false positives. But again, we can see this infrared radiation being utilized in common uses, such as IR vision goggles, night vision goggles. So what we see here are representations of different energy levels, referred to as these energy gaps between the levels. And what we have here on this side, on the left-hand side, is a carbon-hydrogen bond, and the gaps between the different energy levels that exist versus a CO bond, and it has a smaller energy gap that would be needed to promote an electron to a higher energy state. So these different vibrations depend on the type of bond, or rather the energy that's needed to cause these vibrations will depend on the type of bond. So we're going to see that a larger amount of energy can be absorbed by these CH bonds versus the CO bonds, and that will be given in our spectroscopy data, right? So we'll produce this spectrum at the end. So when we have our IR spectrophotometer irradiate a sample with all frequencies of light, so we do not know where an absorption will occur. So we just pick all that's possible within the infrared spectrum. So the frequencies that are absorbed tells us the types of bonds, aka the functional groups present. So if we have, say, an OH stretch, right, between our OH bond here, we know that we would have a alcohol present, right, if we have a hydroxyl group. So there are some techniques that are utilized to place a sample into the infrared spectrophotometer. So we can either use salt plates, such as these sodium chloride plates, because we know that sodium chloride is not going to be reactive in our IR. Also, say we have an insoluble compound that we can dissolve in a solvent and then embed in a potassium bromide pellet. So these are two common techniques that can be utilized with infrared spectroscopy, depending on your sample type. And this here is an example of what an IR absorption spectrum will look like. Our y-axis, the plot of the percent transmitted, is going to be, again, our y-axis here. And we would plot this against the function of frequency. And what we see down here is our unit of wave number. So what wave number is actually the reciprocal of wavelength. So again, this is sometimes designated as nu, which we know is the symbol for frequency, but with a line over top. And this is, again, that symbol that's commonly used for wave number. And a reciprocal centimeter is the unit that is used in this wave number. So again, we mentioned the units of frequency. These are referred to as wave numbers, and we can see that it is the frequency divided by the speed of light, or we could just take the reciprocal of wavelength and generate this in centimeters, right? If we have our wave number, our wavelength in centimeters, we could divide 1 by the wavelength and get the same wave number. So what we see here are that our values range from 400 to 4,000 reciprocal centimeters. And since we know that energy and frequency are directly proportional, this will be our highest energy over here at this wave number. And this will be our lowest energy, around 400 reciprocal centimeters. And everything in between is shown. So again, depending on the type of bond present, we will see this type of image and the percent transmittance shown in different regions. So what other characteristics are there shown in this spectrogram here? So we have not only wave number, so that's given on this scale on the bottom. We also have the concept of intensity, which depending on if you have 0 absorbance up top here, right? Because that would be 100% transmittance would be 0% absorbance. We have down here the opposite. So this would be a fairly strong or intense signal. These that make it all the way down the bottom here. And then these are some mid-range intensities here. We also can comment on the shape, whether something is broad or if something is a narrow signal. So we can see both of those represented here. And we'll describe these in more detail as we move through the chapter.